For a movie released in the 1960s, Stanley Kubrick's 2001 A Space Odyssey was able to achieve scientific accuracy even to the smallest of details. The Space Station 5 was based on the rotating wheel model and is able to generate artificial gravity. To date, the movie is critically acclaimed by many for achieving the best of both science fiction and scientific accuracy. Imagine this: you are in outer space, traveling on a spacecraft. Since there is an absence of normal contact force, you would feel weightless. How then would you be able to feel the effects of gravity? The rotating wheel space station idea proposes that by spinning the space station, and consequently the man, about a rotational axis, by the concept of uniform circular motion, there must be a net centripetal force acting on the man as his linear tangential speed is unchanging. This centripetal force is in the form of normal contact force from the ground of the space shuttle. Hence, the person will feel an apparent weight. Such a method of achieving artificial gravity is highly possible and has been considered by many scientists to be the most viable option for seemingly providing an apparent gravitational force in outer space. Anyway, enough said about the theory and the concept. How can we quantitatively prove that Kubrick's alleged masterpiece is indeed scientifically accurate? This is how. In the movie, it is stated that the rotating Space Station 5 was meant to simulate the gravitational field strength of the moon. This means that the astronaut in the space station would feel an apparent weight of 1/6 his original weight. The gravitational field strength of the moon is 1.6 newtons per kilogram. First of all, let's define the variables in this scene. The radius of the Space Station 5 was conveniently given in a wiki page as 150 meters along its rotational axis. Its rotational period is 61 seconds. With these two variables, we can deduce the angular velocity of the person, since we know that the angle subtended by one complete revolution is 2 pi radians. Hence, angular velocity can be found by the formula omega equals 2 pi over t. Since we know t is 61 seconds, omega equals to approximately 0.10300 radians per second. We have already established that the normal contact force provides the centripetal force required for the astronaut to experience an apparent artificial weight in space. By formula n equals to mass times radius times angular velocity square, which equals to m times 150 times 0.10300 square, we get m times 1.59135. Comparing the variables to the equation F equals to ma, the normal contact force corresponds to F, and m checks out for both equations. Hence, 1.59135 corresponds to the acceleration the astronaut feels in the space station. As said earlier, the acceleration due to gravity of the moon is 1.6 meters per second squared. Hence, the acceleration of 1.59 meters per second felt by the crewman in the space station is an incredibly close figure. Since the apparent acceleration is approximately the moon's gravitational acceleration, the scene is accurate. To think that Kubrick, a director of the new sci-fi film at the time, would have gone to such great lengths to ensure that the dimensions of the space station were accurate is truly something to be applauded and appreciated. It is not difficult for Hollywood movies to be scientifically accurate. All it takes is a little effort and some common sense.